Welcome. So we're going to look today at angular motion and spend more time talking about angular motion. We talked a little bit about this earlier when we talked about uniform circular motion, but we're now going to go into more detail. So we're introducing a concept called angular acceleration. And if you remember, angular motion, imagine a merry-go-round looking down from above. You have some rotation axis in the merry-go-round, and then you have the merry-go-round rotating, in this case, rotating counterclockwise. And in physics, counterclockwise rotation is positive rotation. Clockwise rotation is negative. Angles are typically measured from the positive x-axis, so as this rotates counterclockwise, this angle gets larger with time. That means if something's getting bigger with time, it's a positive change. So positive motion is counterclockwise, negative motion is clockwise. So we have this object rotating, and from uniform circular motion, the object would rotate at a constant rate. There's an acceleration inward, which we call the centripetal acceleration, which is caused by a centripetal force dealing with gravity or tension or something along that line, causing rotational motion. So at each spot, some distance, radius r away from the merry-go-round, an object is traveling at speed v. But I want to put it in terms of rotation now, not in terms of linear motion, but in terms of rotation. So delta theta here is the angular displacement. So at some time t, the point was here. At some later time, it was up here. It moved through some angle delta theta. If delta theta is small, delta theta can be large, delta theta can be multiple rotations. It doesn't have to be between 0 and 360 degrees. It can be more than that. But again, our unit is not degrees. We typically use radians. So it could be between 0 radians. Positive displacement could be 2 pi, 4 pi, 8 pi radians, and so on. Negative displacement, -2, -4, -8 pi rotations. So delta theta is just the angular displacement between 2 points in time. Units are in radians. Now, how quickly delta theta changes with time depends on how fast this thing is rotating. That is the angular velocity. So the angular velocity is given by the Greek letter omega, lowercase omega here. It is in units of radians per second. How many radians does delta theta change in a given amount of time? So the equation for the angular velocity is given up here on the right. Omega, the angular velocity, is equal to delta theta over the change in time. Now for uniform circular motion, we stopped there because this thing was rotating at a constant rate, constant omega. Imagine Earth going around the sun, that occurs once a year, right? Or the Earth rotating on its axis, that occurs once every 24 hours. It is a constant, approximately, angular speed or angular velocity. However, when we talk about angular motion, we can actually change how fast something spins, right? Think of a bicycle. While you're stopped, your wheels aren't spinning, but as you pedal, your wheels start to spin faster and faster. So the angular velocity of a rotating object can change, just like the linear velocity of an object can change. So the angular velocity, we use the Greek letter alpha. It kind of looks like an A, or part of an infinity sign, cut off on the right side. Alpha is the angular acceleration. It has units of radians per second squared. Here's the equation for alpha. Alpha is equal to the change in angular speed, or angular velocity, over time. Note that there's a lot of similarities here between our linear equations. Here, angular displacement is delta theta. Our linear displacement was delta x. Omega here is the angular velocity. It's angular displacement over time. But in our linear case, we had velocity was delta x over time. And then angular acceleration is the change in angular velocity over time. Linear acceleration is the change in linear velocity over time. So the two equations, the two sets of equations, our linear equations and our angular equations, have similar form. And we'll see this pattern continue throughout this section, where we have an equation for linear kinetic energy versus rotational kinetic energy, or linear momentum versus angular momentum. And we'll see how the equations are very similar in structure. So let's look at a little more detail about these three relationships here and how you can get accelerated motion through changing the angular acceleration. Let's look again at a merry-go-round going around in a circle. So we have here a merry-go-round, looking at it from above, or a disk of some sort spinning. Looking at it from above, the central rotation axis is in the middle. This object is moving counterclockwise, and I'm going to speed it up. I'm going to accelerate its motion counterclockwise. So, when an object is experiencing an acceleration, if it's speeding up or if it's slowing down its rotation, it cannot be experiencing uniform circular motion. Uniform circular motion assumes that the rotation speed remains constant, i.e. there is no angular acceleration. But in this example, we're going to put angular acceleration into the system. It might be a bike tire, this is the front tire of a bicycle that's traveling to the left, that's speeding up. So this object is rotating counterclockwise. So omega here, the rotational velocity I have drawn counterclockwise. And it's going to be speeding up. So alpha is also positive because it's moving counterclockwise. Now if I look at some point on the wheel here, at that point, there is a velocity which is tangent to the point. We learned that when we talked about uniform circular motion. There's a velocity tangent to that point depending on two things. Your velocity depends on how fast is this thing spinning. Hopefully that makes sense, right? The faster you have an object rotating, the faster the linear velocity of that object at that point in time. But it also depends on how far away you are from the rotation axis. The way to think about that is if you're standing right in the middle of the merry-go-round, right? You just go around in a boring circle. You really don't have much linear speed. A big enough merry-go-round, you're traveling at an incredibly high rate of speed as that merry-go-round turns. So the linear speed depends on how far away you are from the center, but it also depends on the rotation speed, right? It doesn't matter how far away you are from the center of rotation. If the merry-go-round isn't spinning, you don't have a linear speed. Now this thing that's just from uniform circular motion, that's the same argument. Now this thing is accelerating, which means at that point there's also a linear acceleration tangent to the circle, just like there's a centripetal acceleration inward. So rotational motion tends to have a centripetal force, a centripetal acceleration causing the rotational motion. A sub c is a centripetal acceleration directed inwards. For uniform circular motion, that's the only acceleration there is. But for rotational motion, where the angular acceleration can change, there's another component, a sub t. A sub t is the tangential acceleration. It's perpendicular to a sub c. A sub c is along the radial line of the circle. A sub t is tangent to the circle. So they're 90 degrees apart. And tangent to the circle at the point of interest. So I want to relate these variables, right? We talked about v. V is related to omega and r, but we want to quantify that. So, looking at a couple of equations. We have our centripetal acceleration equation. That's the same as it was for uniform circular motion. A sub c is equal to the speed squared over r. The only difference is the speed now can change with time. For uniform circular motion, the speed was constant. The only thing that changed was the direction of the velocity. The magnitude of the velocity, or the speed, remained the same. But now it can change. So a sub c, if we know what the speed is at a given instant, we can actually calculate what the centripetal acceleration is. Or, looking at the relationship between speed and angular speed, we see that the speed of an object, v, is equal to the angular speed of the object times the object's distance from the rotation axis, in this case, radius of the circle. So linear speed is equal to angular speed times r. Now the units work out too, right? Linear speed is in meters per second. Omega is radians per second. Radian is a non-unit. So it's just basically per second. And times radius in meters, so this becomes meters per second, which is the linear speed. If I plug this into our equation above and square it, right? This is the speed squared. What happens is omega gets squared, r gets squared, the square on top cancels with one of the r's in the denominator here. So the centripetal acceleration in terms of angular velocity is simply equal to the radius times omega squared, where omega is the rotational speed. So no rotation, no centripetal acceleration. And finally, we want to relate this tangential acceleration to the rotational variables as well. Well, tangential acceleration is change in velocity with time, right? That's by definition what tangential acceleration is. We learned about that back when we talked about linear motion. Well, I have an equation here for velocity, or for speed, right? It's omega times r, so I'm going to plug that in here. So the tangential acceleration is equal to the change in omega times r over t. Assuming circular motion, r doesn't change, right? This radius is, all the points on this circle are at radius r away from the center of rotation. So r can come out of that delta. So a sub t is r times the change in omega with time. Well, change in omega with time is the angular acceleration. We learned about that earlier in this video. So the tangential acceleration depends on the angular acceleration times r. Just like the tangential speed depends on the angular speed times r. So see that there's an r relationship between these two types of acceleration and these two types of speed. So here we have the boxed equations, which are important. You'll have to use these to solve homework and exam problems. Centripetal acceleration, tangential acceleration, linear velocity, and another version of centripetal acceleration that deals with angular speed instead of linear speed.